All right, let's jump right into this explainer where we're going to model energy as the dynamic, completely interconnected, universal currency of the physical world. You see, if you really want to understand how the universe operates at a fundamental level, you kind of have to understand its economy. And in grade 8 physical science, well, not economy is all about energy. We're going to look at exactly how this currency is spent, saved, exchanged, and yeah, even taxed by the environment.
Here's a quick look at our roadmap for today. We'll start with the universal energy system, then move to doing work and generating power. After that, it's kinetic and potential energy, followed by conservation and simple machines, heat transfer and system loss, and we'll wrap it all up with a recap and a final transfer question.
Okay, part 1. The universal energy system, the currency of the universe. So at its core, energy is simply the ability to do work. Think of it exactly like a currency that can be stored, spent, and exchanged everywhere in the universe. It's measured in a unit called joules, named after the physicist James Joule. Just like you can have, dollars sitting in a bank account or cash in your wallet ready to go, you can have energy stored up or actively being used. But to actually buy any real physical changes in the world, you have to spend those joules.
Which brings us to part 2, doing work and generating power. Spending the currency.
Now, in physics, work has a very strict literal definition. You must apply a force to move an object over a distance in the exact direction of that force. The formula is just work equals force times distance, meaning if you aren't actually moving something by pushing or pulling it, you aren't scientifically doing work, no matter how exhausted you might feel. You are only spending your energy currency if physical distance is being covered by your force.
And here's a brilliant way to visualize that exact concept. Imagine lifting a heavy rock straight up from the ground. That is work. You're applying an upward force against gravity, and the rock is moving upward. Perfect. But imagine carrying that exact same rock forward across a lawn at a steady, constant speed. Believe it or not, that is entirely not work. Why? Well, the force you're applying is upward, just to keep the rock from falling, but the movement is forward. Since there's no net forward force being applied to keep it moving at a constant speed, scientifically, zero work is being done on that rock. Wild, right?
So, if work is spending the currency, power is simply how fast you spend it. Power is the rate at which work is done, calculated as work divided by time, and we measure this in watts. Basically, if you accomplish the exact same amount of work in a shorter amount of time, you are generating more power.
Let's look at a super practical example. Picture lugging a heavy TV up 4 flights of stairs, which takes, say, 5 exhausting minutes. Now picture using a pulley machine to hoist that identical TV up outside the window to the exact same floor, taking only 2 minutes. The total work done, the force needed to overcome gravity over that specific vertical distance is exactly the same, but the pulley allows you to do that identical work in way less time. That means you're generating more power. This is why simple machines are so incredible. They literally let us manipulate this physical exchange rate.
Moving on to part 3, kinetic and potential energy, the 2 forms of currency.
Mechanical energy basically comes in 2 primary forms. First, we have potential energy, which is your stored currency. Gravitational potential energy depends entirely on an object's mass and its height. Think of a roller coaster car pausing for that agonizing second at the very top of a massive hill. It is fully loaded with potential energy. Then we have kinetic energy, which is the active currency of motion. The second that coaster drops and speeds up, all that stored energy transforms directly into the energy of movement. As that roller coaster speeds down the hill, notice this beautiful inverse relationship happening. Exactly halfway down the drop, assuming a perfect world with no friction, the stored potential energy is perfectly converted into kinetic energy. It's an exact 50-50 split. The total amount of energy hasn't changed at all. It's simply being transferred from the savings account of height over to the checking account of speed.
Okay, time for our first pause check. Take a quick beat to think about this one. If a 10-kilogram rock falls from a 20-meter cliff, what happens to its kinetic and potential energy exactly halfway down the drop, right at the 10-meter mark?
The answer? They are perfectly equal at 980 joules each. Here's the immediate reasoning for that. At the top of the cliff, its potential energy is its mass times gravity times height. So, 10 kilograms times 9.8 meters per second squared times 20 meters, which gives us an initial 1960 joules. Exactly halfway down, half of that vertical height is gone. That means exactly half of that potential energy, 980 joules, has transformed perfectly into kinetic energy.
Let's dive into part 4, conservation and simple machines, the closed system.
This brings us to a massively crucial point, the law of conservation of energy.
It states that in a closed system, meaning a theoretical setup where we completely ignore outside friction or air resistance, the total sum of mechanical energy never, ever changes. Energy literally cannot be created from nothing, and it absolutely cannot be destroyed. It just changes forms, constantly shifting from potential to kinetic and back again.
Let's do our second pause check to test this law. Imagine an ice skater smoothly gliding along at 8 meters per second. Suddenly, a friend comes up from behind and gives her a solid push, increasing her speed to 12 meters per second. She now clearly has way more kinetic energy than she did a second ago. Does this newly gained energy violate the law of conservation? The answer is absolutely not, and here's the immediate reasoning why. The friend actually did work on the skater system. They actively applied a force over a distance, and according to the work-energy theorem, the work done directly equals the change in kinetic energy. So the energy wasn't magically conjured out of thin air, it was simply transferred from the friend's muscles straight into the skater's motion. The system as a whole still perfectly balances. Moving on to part 5, heat transfer and system loss, the environment tax. So, in real, everyday life, energy is often taxed and escapes our closed systems as thermal energy, or what we commonly just call heat. This happens through 3 main methods of heat transfer. First up is conduction, which is direct physical contact. Think of a hot pan touching a stove. Second is convection, which is the movement of fluids or gases, like hot air rising in a room. And third is radiation, which transfers heat via electromagnetic waves without needing any medium at all, like feeling the sun warming your face. So whenever friction occurs in a machine, kinetic energy is effectively taxed and bleeds out into the surrounding environment through these exact methods.
And what's wild is that different materials absorb this heat tax very differently. This is a property known as specific heat. Notice how water requires a whopping 4,186 joules of energy just to raise 1 kilogram of it by a single degree Celsius. But look at glass. It only takes 840 joules. That means it takes roughly 5 times more energy to heat up water than glass. This incredible stubborn property of water is actually what stabilizes Earth's entire climate.
Finally, part 6, recap and final question, applying the model.
Let's quickly pull this whole coherent system model together. Work is exactly how we transfer energy by applying force over a distance. Power dictates the speed or the rate of that transfer. Potential and kinetic are the actual physical forms of this currency. Simple machines allow us to cleverly alter the physical exchange rate of power and work. Heat is the unavoidable environmental tax caused by friction. But overall, zooming way out to the universe as a whole, total energy is perfectly, beautifully conserved.
I'm going to leave you with this transfer question to really test your grasp on our new system model. When a massive 10,000 kilogram truck rides its brakes all the way down a steep hill, just to maintain a constant speed without accelerating, exactly how is its gravitational potential energy becoming a highly dangerous heat tax? Think closely about the conservation of energy and where all those millions of joules have to go if they aren't becoming kinetic motion. Ponder that for a bit. Until next time, keep exploring the incredible mechanics of our universe.